Hello students, welcome to EPG Pathshala. I am Sumalay Roy from the Department of Physics and Astrophysics of Delhi University. Today we are going to discuss about the module examples illustrating use of degenerate perturbation theory from the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. We will learn to use degenerate perturbation theory in the case of a simple two-dimensional harmonic oscillator, which is a two-fold degenerate in the first excited state. We will know how in the presence of a perturbation, this degeneracy is removed to yield the energy levels and the corresponding eigenstates. We will use the degenerate perturbation theory in a three-dimensional cubical well, where in the first excited state, it is threefold degenerate. We will learn to use of degenerate perturbation theory in Stark effect, where in the hydrogen-like atoms, the first excited states are fourfold degenerate, and the presence of externally applied electric field removes that degeneracy only partially. In this module, we consider a few typical examples to illustrate how degenerate perturbation theory developed. In the preceding module is used and the degeneracy is removed in the presence of perturbation. We start with a simple example of a two-dimensional simple harmonic oscillator, which in the first excited state is twofold degenerate. And we see how the degeneracy in the energy levels is split due to perturbation. The next example is of a three-dimensional infinite cubical well. Here, the first excited state is triply degenerate. We find the expressions for the energy levels and the corresponding eigenfunctions due to a potential which acts as a perturbation. Third example is a well-known Stark effect, where the applied electric field along the z-axis on the hydrogen atom, hydrogen or hydrogen-like atoms, acts as a perturbation and splits the energy level of the first excited state, which is fourfold degenerate. We show that their degeneracy is partially removed. The two-dimensional harmonic oscillator. Now consider a two-dimensional harmonic oscillator with total Hamiltonian H equals to H0 plus H prime, where H0 is equals to Px square by 2m plus Py square by 2m plus half m omega square into x square plus y square. That means it is two dimension, and here H0, Px, Py all are operators. And H prime, which is the perturbation Hamiltonian, is given by lambda multiplied by m into omega square xy. Here, the unperturbed eigenvalues are given by E n1 n2, which is equal to n1 plus n2 plus 1 into h bar omega, where n1, n2 can take only 0 and integers like 0, 1, 2, 3 and so on and so forth. And omega is the angular frequency, which is given by square root of k upon m. The corresponding normalized eigenfunctions are psi 0, n1, n2, nh n1, alpha x, here h is a Harmonic polynomial, exponential minus alpha square x square by 2, hn2 alpha y, exponential minus alpha square y square by 2, where alpha is actually m into k by h bar square to the power 1 by 4, and capital N is alpha by square root of phi into square root of 1 by 2 to the power n1 into n1 factorial into 1 by 2 to the power n2 into n2 factorial. This whole under a square root. The ground state corresponding to n1 equals to 0 and n2 equals to 0 is non-degenerate. However, the first excited state where n1 equals to 1 and n2 equals to 0 and n1 equals to 0 and n2 equals to 1 has the same energy E equals to 2 h bar omega. Writing the eigenfunctions explicitly for these values, we have psi 0 0 0, that means the ground state n1 equals to 0, n2 equals to 0 and ground state 0 equals to alpha by square root of pi exponential minus alpha square x square by 2 into exponential minus alpha square y square by 2. Psi 01, psi 001, which means the ground state with n1 equals to 0 and n2 equals to 1. This is given by alpha by square root of pi into 1 by 2 to the power half exponential minus alpha square x square by 2 into 2 alpha y into exponential minus alpha square y square by 2. Psi n1 equal to 1, 2 equal to 0, that means ground state psi, which is psi 0, n1 equals to 1 and n2 equals to 0, is given by alpha by square root of pi into square root of half 2ax exponential minus alpha square x square by 2 exponential minus alpha square y square by 2. Similarly, when n1 equals to 1 and n2 is equal to 1, then psi 0 is given by alpha by square root of pi into 1 by 2 into 2 alpha x into exponential minus alpha square x square by 2 into 2 alpha y into exponential minus alpha square y square by 2. Therefore, this state is doubly degenerate. So we have a doubly degenerate harmonic oscillator. It is easy to see that when this oscillator is subjected to the perturbation given by 30.2, we have h11 prime equals to m omega square into integral of psi 100 star of xy into psi 010 to dx dy equal to 0, and so is h prime equals to m omega square multiplied by the integration of psi 0 star 01 into xy to psi 01 of 0 ground state dx dy equals to 0 because of parity considerations. We can also easily verify that h12 prime equals to alpha by square root of pi whole square 1 by 2 into lambda m omega square into double integration of 2 alpha x exponential minus alpha square x square by 2 into exponential minus alpha square y square by 2 into xy into exponential minus alpha square x square by 2 into 2ay exponential minus alpha square I square by 2 into dx dy, which is again equal to alpha by square root of pi multiplied by lambda m omega square by 2 into alpha square into integration minus infinity to plus infinity to x square into exponential minus alpha square x square into dx, this whole square. This gives h12 prime is equal to lambda into h bar omega by 2, which is h21 prime. Thus, on solving the secular equation, we find the two values of W1 are plus h bar omega by 2 and minus h bar omega. As a result, the energy level splits into the doublet 2h bar omega plus h cross omega by 2 and 2h bar omega minus h bar omega by 2. The zeroth order eigenfunctions associated with the first of these may be found by setting W1 equals to H12 prime in the equation H11 prime minus W1 into C10 plus H12 prime into C20 equals to 0, which gives C10 by C20 equal to plus 1. Thus, the normalized eigenfunction is psi 10, which is 0 ground state, plus psi 010 equal to into divided by square root of 2. For the second or the lower member of the doublet, W1 equals to minus H12 prime. That gives C10 by C20 equals to minus 1. So the zeroth order wave function is psi 010 minus psi 001 whole divided by square root of 2. Three-dimensional infinite cubical well. Let us consider an example of the three-dimensional cubical well of potential V has a function of x, y and z equals to 0 if 0 less than x less than a, 0 less than y less than a, that means x and y lies between 0 and a, and similarly z, that is vxy is equal to 0 and v equals to infinity otherwise. The stationary states are psi 0 ground state nx, ny, nz as a function of x, y, z is equal to 2 by a to the power 3 by 2 sine nx pi by a into x into nx pi by a into y into ny nz pi by a into z, where nx, ny and nz are positive integers. The corresponding allowed energies are E nx, ny, nz 0 equals to pi square h bar square by 2m square into nx square plus ny square plus nz square. Clearly, the ground state psi 0111 is non-degenerate. Its energy is E00 equals to 3 into pi square h bar square by 2m square. However, the first excited state is triply degenerate. So, the energy which was a single excited state, the first excited state, now becomes three energy states, which is triply degenerate. Psi A equals to, which is equivalent to psi 112, psi B, which is equivalent to psi 121, and psi C, which is equivalent to psi 211, all belonging to the same energy E10 equals to 3 pi square h bar square by m square. Let us now introduce the perturbation, which is h prime equals to v0 if x is within 0 and a by 2 and y is within 0 and a by 2 and h prime is 0 otherwise. Now in the figure we show a cube, the perturbation introduced by the potential indicated by the red boundaries in the cubical box. The red boundaries are at a by 2 as seen in the figure. The first order correction to the ground state energy is given by E01 equals to the matrix element of H prime between psi 11 and psi 11, which is given by 2 by a whole cube V0 integration 0 to a by 2 psi square pi a into x dx into integration 0 to a by 2 psi square pi a by y pi by a into y dy into integration 0 to a psi square pi by a into z dz. Now if we calculate all this integration, it comes out to be 1 by 4 into V0. The integral in 30.19 can be easily evaluated. Note that the upper limit of the integration over the variable z extends from 0 to a, whereas for variables x and y, they are from 0 to a by 2. To construct the matrix of the secular equation, we find that the diagonal matrix elements are the same as for the ground state, except that the argument of one of the sides is doubled. Thus, WA equals to WBB equals to WCC, that is 1 by 4 into V0. As for the off-diagonal elements, we proceed as follows. WAB, which is equal to 2 by A whole cube V0 into 0 into integration 0 to A by 2 for x, which is sine square pi by A into x dx, 0 to A by 2 sine pi by A into y into sine 2 pi by A into y into dy, and for z 0 to A sine 2 pi by A into z into sine pi by A into z dz. As is clear from 30.21, the integral over z is 0. This will also be true for the off-diagonal element WAC. Thus, WAB equals to WAC, they are all 0. Finally, WBC equals to 2 by A whole cube into V0 integration 0 to A by 2 sine pi by A into x sine 2 pi by A into x dx into integration 0 to A by 2 sine 2 pi by A into y sine pi by A into y dy into integration 0 to A sine square pi by A z into dz. Now if we evaluate the integrals, it comes out to be 16 by 9 into pi square is whole equal to V0. Let us first write down the matrix W, which is W equals to V0 by 4. The first row, first column element is 1. The first row, second column element is 0. The first row, third column element is 0. The second row, first element is 0. The second row, second element is 1. The second row, third column element is eta. Also, the third row, first column is 0. Third row, second column is eta. And third row, third column is 1. Now, this is the matrix W, where after taking V0 by 4 as common factor, we redefine WBC equals to WCB equals to eta, and eta is equal to 8 by 3 pi. The secular determinant, apart from the factor V0 by 4, appears as 1 minus omega as the first row first element, first column element, 0 for the first row second element, and 0 for the first row third element. And second row first element is 0, second row second element is 1 minus omega, and second row third element is eta. Third row first element is 0, third row second element is eta, and third row third element is 1 minus omega. This total determinant is 0, which can be easily worked out to give 1 minus w to the whole cube minus eta square into 1 minus w equals to 0. Thus the roots for w are w1 equals to 1, w2 equals to 1 plus eta, and w3 equals to 1 minus eta. Translated back in terms of the original notation, the first order correction in the perturbation energy gives E1 lambda equals to E10 plus lambda into V0 by 4, E10 plus lambda into 1 plus eta into V0 by 4, E10 plus lambda into 1 minus eta into V0 by 4, where E10 is the common unperturbed energy given between 30.17. The perturbation removes the degeneracy, splitting E10 into 3 distinct energy levels. You can see in the figure 30.2, where E1 lambda is plotted as a function of lambda, and when lambda is equal to 0, we have one particular point E10, which means that for lambda equal to 0, which is non-degenerate state. Now when an increase of lambda, this state splits into 3 different energies which is shown by 3 different lines till lambda is equal to 1. As for the good unperturbed states, psi 0 is equal to C1 psi A plus C2 psi B plus C3 psi C, where the coefficients C1, C2, C3 form the eigenvectors of the matrix W, which is the matrix 1, 0, 0, 0, 1 eta, 0 eta 1, multiplied with the vector C1, C2, C3 is equal to W into C1, C2, C3. Solving this matrix equation, we have for W equal to 1, C1 equal to 1, C2 and C3 equals to 0. Similarly, for W equals to 1 plus minus eta, we get C1 equals to 0, C2 is equal to plus minus C3, and which is again equal to 1 by root 2. Now, thus, psi 0 is, one is psi A, another is psi B plus psi C by square root of 2, and psi B minus psi C by square root of 2. Stark effect. Stark effect, the effect of an electric field on the energy levels of hydrogen atom. Now, when an atom is placed in a uniform external electric field, which is designated as capital E external, the energy levels are shifted. This phenomena is known as Stark effect. Here we analyze the Stark effect for the n equals to 1 and equals to 2 states of hydrogen atom. Let the field point along the z direction. So the potential energy of the electron of charge minus E in the field is H prime equal to E small e, which is electronic charge, E external, and the Z, which is again minus E into E external into R cos theta. The effect of this additional interaction energy on the atomic energy levels is investigated using the perturbation theory. The ground state. Since the ground state psi 1 SR is nothing but equal to psi 100 R is non-degenerate, it follows that the first order correction to the energy is E first level energy 1 E1 superscript 100 equals to small e multiplied by E external and the expectation value of Z within psi 100 states. Now that is equal to E into E external integration modular square of psi 100 R into Z into dr. Consider in general the integrals I NLM, which is integral of modular square of psi NLM R into Z into dr. Under the interchange of R to minus R, we have I NLM equals to integral of modulus of psi NLM minus R modular square minus Z into dr. We know that the hydrogenic wave functions have the parity minus 1 to the power L. That is, psi NLM minus R is equal to minus 1 to the power L psi NLM R. From this it follows that psi NLM minus R modular square is equal to psi NLM R modular square. Therefore, comparing equation 30.34 to 30.35, we find I NLM is nothing but minus of I NLM. So that I NLM is 0. This goes to prove that first order energy shift given by 30.33 is 0. The second order term of the perturbation given by E1002 is equal to E square Ez square sum over n, which is not equal to L, and then sum over L and M, and then modular square of expectation value of Z in the state psi n Lm by E1 minus En, where the summation is over all the discrete set of the hydrogenic eigensets. as well as with an integration over the continuous state set. From 30.38 we see that since the energy difference E1 minus En with n greater than equal to 2 are always negative and E100, that is first excited state 100, is 0. The ground state energy is always lowered by the interactions with the electric field. For atomic hydrogen, therefore, the quadratic Stark effect 30.38 is very small. Let us examine the first order Stark effect for the first excited state of hydrogen atom. Now the n equals to 2 energy level. This has a fourfold degenerate because of each of the 4 eigenfunctions: psi 200, psi 2100, psi 210, psi 211 and psi 21 minus 1. These all are corresponds to the same energy En minus 2. En equals to 2. Therefore, we have to use degenerate perturbation theory. In principle, we have to solve a system of 4 homogeneous linear equations. However, we notice that minus Ez is the z components of the electric dipole moment operator. As a result, the matrix element of the form n prime, l prime, m prime and within z and nlm vanish unless l prime is equal to l plus minus 1 and m prime equal to m. Thus, the only non-vanishing matrix elements of the perturbation H prime is equal to minus E into capital E external Z between the 4 states of 30.39 are those which connect the 2s2200 and 2p0210 states. It follows that the linear homogeneous equations given in the preceding module reduce to a set of 2 equations. The 2 equations are minus ER1 CR1 plus H12 prime CR2 equals to 0, and the next one is H12 prime CR1 minus ER1 CR2 equals to 0, where R is equal to 1, 2, and the matrix element H12 prime is given by H12 prime is equal to H21 prime, which is again equal to E into E external integration of psi 20R Z into psi 200R dr. The condition for the non-zero solution of the equation 30.40 is that the determinant minus ER1 H12 prime H21 prime and minus ER1 is equal to 0. The roots of this equation are ER1 is equal to plus minus modulus of H12 prime. Now, to evaluate the matrix element H12 prime, we use the hydrogenic wave function 2s and 2p0. Thus we get H12 prime is E into E external z cube by 8s0 to the power cube 8s0 to the power 3 2 by 3 into integration 0 to infinity dr r cube into zr by a0 into 1 minus zr by 2a0 into exponential minus zr by a0, which gives us minus 3 into E into capital E external A0 by Z. Clearly, the change in energy is directly proportional to the external electric field Ext. It is therefore called the linear Stark effect. The effect is non-zero only for degenerate state of hydrogenic atoms from 30.40. We see that for the root E1 equal to modulus of H12 prime, we have C11 equal to minus C12. The corresponding normalized wave function is therefore psi 10 is equal to 1 by square root of 2 into psi 200 minus psi 210. The second root E11 equal to minus modulus of H12 prime yields C21 equal to C22, and the normalized wave function is psi 20 is equal to 1 upon square root 2 into psi 200 plus psi 210. We notice that the wave function 30.45 and 30.46 are neither eigenfunctions of parity nor of L square. Thus, neither parity nor L is a good quantum number. This figure depicts splitting of the degenerate n is equal to 2 energy level of hydrogenic atom due to linear Stark effect, which shows that there are 4 degenerate states as L equal to 0, M equal to 0, L equals to 1, M equal to 0 and plus minus 1. It splits into 4 different states like M equal to 0, M is equal to plus minus 1 and M equals to 0. The corresponding wave functions are tabulated on the right hand side. From the figure, it is clear that fourfold degeneracy is partly removed by the perturbation, which is along a particular z direction of space. The energies of the 2p plus minus 1, that is 2, 1, 1 and 2, 1 minus 1 states remain unaltered. Thus the level splits symmetrically into 3 sublevels, one of which corresponding to M is equal to plus minus 1 is twofold degenerate. In this module, we have learned that to use degenerate perturbation theory in the case of a simple two-dimensional harmonic oscillator, which is twofold degenerate in the first excited state. We learned to use the degenerate perturbation theory in a three-dimensional cubical well, where in the first excited state it is threefold degenerate. We have learned the use of degenerate perturbation theory in Stark effect, where in hydrogen-like atoms, the first excited states are fourfold degenerate, and the presence of externally applied electric field removes the degeneracy only partially. Thank you.